Okay, here goes. We are going to try t-tests. First thing to do, descriptive statistics. Now, I'm going to go get my descriptive statistics tab. I'm going to data. There I have data analysis. If you can't find the data analysis tab, you go here, go into options, go into add-ins, go into manage Excel add-ins, and you need to make sure these two tabs have a check mark. And when they do, your data analysis tab will appear here. So there we go. We have our data analysis tab. Go to descriptive statistics and say OK. I'm going to select the input range. This data here. I have my labels checked in the first row. My output range is going to appear here. And I have these two boxes checked. Excellent. Let's say OK. And there I have control and experimental. I'm going to double click to expand. Now I'm going to use the means from this table by selecting the mean, numerical mean, and holding control and selecting that at the same time. I insert a graph and I will switch row and column. I'm going to select, first I'm going to delete this. I'm going to select here, and that is the mean that's showing up. I'm going to add error bars. Move my webcam out of the way. I'm going to select error bars. And what I want to do is customize what error bar I'm going to include. So I scroll down to my custom option, specify my value to the standard error of the mean, and say OK. And I'll do the same for the other. And my error bars, more options. And again here I'm selecting standard error mean. And say OK. What this shows me is that my means will never always be the same should I repeat my experiment, but they'll fall within this range. That's what standard error means. Now, I am going to choose a t-test to compare the means to see if they're significantly different. Now, the error bars give you a good indication that they are significantly different. But right now, I'm going to do a t-test to get a p-value to be very specific about that. Now, which t-test shall I use? Data analysis, because look at how many there are. Paired, unpaired, assuming equal variance, and unpaired, equal and unequal variances. So what do? Well, I am going to choose paired in this case. In this case, why? Because we have kids that are the same kids before and after an experiment. In this case, the kids are receiving breaks in the experimental case, and their test scores go up compared to the controls, it seems, by a quick glance. So let's look at paired in this case, because it's the same individuals before and after treatment. My input variable range for here is exactly this. It's been selected already. Yes. And my input variable range 2 is the experimental. So selecting. And my labels are in the first row, and I have an output range. I say OK. And the value that interests me are these p-values. So I have a p-value here and a p-value here. I would have predicted that the kid getting a break would have scored higher. I believed it went in a particular direction. Not just that there was a difference, but the difference was in a particular direction, favoring higher scores for the experimental. So in that case, this is my value of interest. So because p-value, which is equal to 0.003711 is less than 0.05, the means are significantly different. Therefore, the breaks, the regular breaks, increase scores. Increase grade, increase scores. Let's just say grade. Good. Now let's do a unfair t-test. Here we have a situation where, again, we're going to compare means. We have 24 female rats altogether. 12 were fed on a high protein diet, 12 completely different ones on a low protein diet, and we measure their weight gain between 28 and 84 days. So we're going to now do, again, we always start with descriptive statistics. Descriptive statistics and say OK. The input range here is data, including the labels. The label box is checked. The output range, D3 up there, is fine. And the summary statistics box and confidence level mean is checked. So that's great. And I'm going to graph the same way. I'm going to insert column graph. Yes. And I'm going to switch row data. This is chart title, but title should go on the X and Y axes. Add my error bars. In order to do that, I'll move this out of the way. Add error bars. More options. I find my custom value to specify. Here, standard error mean again. And then we say OK. Oh, lovely. And now next, add error bars once again. My options. Custom value, specify value here. And now I get a sense of how much overlap the values have, and not very little. So here, if I were to repeat the means, they would likely still be different. But now we need to do a t-test to get a p-value. Now, which t-test shall I use? Go to data. And again, here you see there are 3 kinds of t-tests. Now, because these rats are different, these rats here are completely different than these rats that are in this set of data. We're going to not use paired, we're going to use the unpaired, the 2 sample, either equal variances or unequal variances. In order to determine which of the variances we have, we could do one thing. Look at our sample variance here and here. Of course, they're not exactly equal, but we need to know if they're significantly different. So we select the F test for that. In order to do that, we're going to, there we go, select the high protein versus the low protein, which is, there we go. The output range, A20. That's good, like a good place to put it. Labels are there. Excellent. So now we have an F test. So here's critical, and there's our F. Our critical is bigger than the F. And so they are considered significantly different. And here's another value. There's our p-value. Because the p-value in this case is p-value larger than 0.05. That means that variance is significantly different. Let me just check. What we need to do now is then choose unequal variance, a t-test for unequal variances. So we say OK. Input variable range 1 will be this, high protein, versus input variable range 2, low protein, labels in the first row, output range, select inside the output box, and I am going to put my value down here somewhere. This is fine. Okay. So now I have my t-test. I expected a difference, so I will again go with the one tail, and there is a significant difference again, showing that, which supports, of course, what we see in the figure, which is no overlap for the error bars. So here we have a p-value smaller than 0.05, and therefore the differences we're seeing are not due to probability of sampling error. So here, p-value is less than 0.05. So I can say differences in the is not due to sampling error. And therefore is significant. I hope this helped.